In the deep quiet of space, nothing seems to rush. Stars turn on their axes with stately slowness. Galaxies stretch across the void, their motions measured in hundreds of millions of years. Black holes drift like shadows in a dark room. Everything moves, but it moves with the patience of time itself, a slowness that can make eternity feel tangible. And yet, even this profound stillness has a direction. Even silence can lean toward something. This is the story of black holes that do not remain alone. Most black holes begin in solitude. Born from the collapse of a single massive star, they sit in the dark of interstellar space, pulling gently on whatever dust, gas, or unlucky star wanders too close. But some, especially the supermassive giants at the centers of galaxies, are not destined for a life of isolation. Because galaxies themselves are not static. They orbit within clusters, they sway in the gravitational currents of the cosmos, they drift, and sometimes they collide. The word collide can be misleading. It conjures images of a cosmic car crash, a violent, fiery smash. But that is not the way of galaxies. Galaxies are mostly empty space. They contain billions of stars, yes, but the distances between those stars are immense. When two galaxies merge, it is not a smash but a slow, graceful dance, a weaving of stars and dust, a gentle pulling of spiral arms, a bending of motion that unfolds over billions of years. From our distant vantage point, it is one of the most beautiful sights in the universe. Two spirals becoming tangled, their structures dissolving into a new, often elliptical, shape, with long, luminous tidal tails of stars thrown outward like glittering streamers in the cosmic dark. And at the heart of each galaxy, a supermassive black hole. When galaxies begin their merger, these central black holes are initially far apart, separated by tens of thousands of light years. They are each the king of their own castle. But as the stars and dark matter of the two galaxies swirl and mix, as orbits are reshuffled in a grand gravitational reorganization, a slow, inevitable process begins. The two black holes, the heaviest objects in the new, combined system, begin to sink. Drawn by dynamical friction, a kind of gravitational drag from the surrounding stars, they drift toward the common center of the new, larger galaxy. It is a process of immense patience. It can take 1 billion years or more for them to even notice each other directly. They are like two mighty ships, each caught in the same vast, slow-motion whirlpool, gradually drawing closer with each circuit. But once they do get close enough to feel each other's gravitational influence, within a few light years, the final act of their dance begins. This is the part we have been waiting for, the binary spiral on a supermassive scale. At first, they orbit each other, two invisible titans waltzing in the crowded stellar core. They transfer energy to the surrounding stars, kicking them out into wider orbits, which allows the black holes to spiral even closer. This is a slow, stately tightening. Then, as the space between them narrows to less than a light year, a new force takes over, the emission of gravitational waves. Just like their stellar mass cousins, these gigantic black holes, as they orbit, stir the space-time around them, sending out ripples. These waves carry away orbital energy, causing the black hole's paths to tighten further, their dance to accelerate. The spiral becomes a fall. The fall becomes an embrace. Why do they merge? Why not just orbit each other forever? The universe, in its elegant economy, does not allow for perpetual motion. Every orbit carries kinetic energy. To merge, to come to rest as a single object, that energy must go somewhere. In the final stages, gravitational waves are the universe's release valve, carrying the colossal energy of the inspiral away into the cosmos. You could imagine it like two whirlpools in a river, separate at first, but caught in the same current. The spiraling water around each one interacts, pulling them together. Eventually, they merge into a single, larger, more powerful whirlpool. Their identities consumed by a new, unified structure. These galaxy-scale mergers are not rare accidents. We believe they are a fundamental part of cosmic evolution, a primary way supermassive black holes grow to such immense sizes. One black hole finds another. They merge. That new, larger black hole may, in another few billion years, meet another. A cosmic cycle of quiet, immense unification. We look for the signs of these impending unions. Sometimes we see two bright, active galactic nuclei close together, each flickering with the X-rays of a feeding black hole, a sure sign of two galactic cores nearing their end. Other times we see galaxies with bizarre, distorted shapes, the telltale signs of a gravitational tug-of-war. And in the future, we will not just see them, we will hear them. The gravitational waves from merging supermassive black holes are too low frequency and long period for LIGO to detect. They are a deep bass note to LIGO's high chirp. To hear them, we need to go to space. Projects like the Laser Interferometer Space Antenna LISA, a planned mission by NASA and the European Space Agency, aim to do just that. Imagine 3 spacecraft, millions of kilometers apart, flying in a perfect triangle, connected by laser beams. They would form a gravitational wave observatory with arms far longer than any possible on Earth, tuned to the low-frequency rumble of the universe. LISA would be able to hear the final millennia of the dance between supermassive black holes, the slow, rising crescendo that culminates in the most energetic events since the Big Bang. So tonight, imagine 2 such black holes. One was born in a spiral galaxy, the other in an elliptical. They drifted for eons, unaware of each other's existence. They circled in the silence of their own domains. Now, drawn together by the merged gravity of their combined galaxy, they move as one. Invisible to any eye, but impossible to stop. You don't need to rush. They don't. Their spiral takes its time, but its end is as inevitable as gravity itself. And when it comes, it will send a tremor through space-time that will outlast the stars. But this grand external dance leads to an even deeper, more perplexing internal question. As they merge, as their event horizons touch and flow into one another like 2 drops of water, what happens to what's inside? What happens to the stars they have consumed, the particles, the photons, the very information that crossed their thresholds? Does a black hole ever reveal its secrets? Or does it forget truly and utterly? Let's float gently and humbly toward that mystery next, to the edge of physics itself. There are questions that science can approach, measure, observe, and test. And then there are questions that hang like stars just beyond our reach, visible but distant, real but wrapped in a shroud of mystery. The question of what happens inside a black hole is one of those. It is a whisper at the very boundary of our understanding, a frontier we know is there but cannot cross, not even in our imagination, without our maps of reality beginning to fold and tear. Still, tonight we can drift close to the edge. We can look into the darkness and wonder. You remember the event horizon. It is the surface of no return. It is not a physical wall, not a hard shell you could bump into. It is a region in space, a mathematical boundary defined by gravity's ultimate victory over light. If a particle of light, a photon, crosses it, it can no longer climb out. Its future, from that moment on, lies inexorably inward. If time itself could be said to have a direction, it too bends inward at this threshold. From the outside, the event horizon presents a strange and ghostly spectacle. Imagine watching an astronaut, brave and foolish, falling toward a black hole. From your safe, distant perspective, you would see something bizarre. As they approach the event horizon, their signals would slow down. Their clock would appear to tick more and more slowly. Their image would stretch and redden, fading to a dim crimson smear. They would appear to slow, to freeze, suspended forever just at the threshold. their image etched onto the horizon for all time before eventually fading to black as their light becomes too dim and redshifted to see. To you, the outside observer, the fall never truly concludes. It is a journey that asymptotically approaches an end, but never, from your viewpoint, reaches it. But from the falling astronaut's point of view, the story is starkly different. There is no sudden jolt, no dramatic line to cross. They would drift through the event horizon without any local sensation, any flash or bang. It is an invisible threshold. But from that moment on, every possible path, every future, leads inward toward the center, the singularity. There is no turning back. Not because a force is holding them, but because the very geometry of space-time has become so warped that out is no longer a direction that exists. That center, the singularity, is not a place in any way we can comprehend. It is a point where our current laws of physics, the very equations of general relativity, break down. Density becomes infinite, space-time curvature becomes infinite. It is not that we've hit a wall. It is that the road ends and the map turns to nonsense. Our understanding of reality dissolves into a shower of infinities. We don't know what happens there. Some theories suggest that the rules of quantum mechanics, which govern the very small, might smooth out this infinity into something else. A Planck scale structure, a fuzzball, a something still mysterious but not infinite. Others believe an entirely new theory of quantum gravity, one that unites Einstein's relativity with quantum mechanics, is needed to explain it. But for now, the singularity remains the ultimate here be dragons on our cosmic map. Here is something even stranger. Inside the event horizon, the roles of space and time seem to swap. Outside, you can move freely in space but are carried inexorably forward in time. Inside, the radial direction toward the singularity becomes more like time itself. You don't fall through space. You are carried into the future, and that future, in the grim geometry of the black hole, ends at the singularity. No matter how you twist or turn, it is your future that draws you there. Your path is not just physical, it is temporal. This leads to one of the greatest conundrums in modern physics, a paradox that has divided theorists for decades: the information paradox. You see, quantum mechanics, the other pillar of modern physics, has a fundamental rule. Information cannot be destroyed. Information, in this sense, is the complete specification of a system, the position, momentum, spin, and type of every particle. Quantum mechanics says this information can be scrambled, transformed, made incredibly difficult to read, but it can never be truly erased. It is a law of conservation, like the conservation of energy. Black holes, however, seem to be the ultimate shredders. Once something crosses the event horizon, all the intricate information about what it was, whether it was a diamond, a book, or a hapless astronaut, seems to be lost forever. All that remains, from the outside, are three simple properties: mass, electric charge, and spin. This is known, poetically, as the no-hair theorem. A black hole has no hair, no frizz, no details, no individuality beyond these three numbers. It is the ultimate simplification. So where did the information go? Is it truly destroyed at the singularity, violating a cornerstone of quantum mechanics? Or is it somehow preserved? This is the information paradox. Stephen Hawking famously thought that information was lost, which would require a fundamental rewrite of physics. This sparked a decades-long debate. Today, many physicists lean toward the idea that information is, in fact, preserved. But how? Some of the leading ideas are mind-bending. The holographic principle suggests that all the information about what fell into a black hole is not lost inside, but is somehow encoded on the two-dimensional surface of the event horizon, like a cosmic hologram. The three-dimensional interior is a projection of this information stored on its boundary. Another idea is that information slowly leaks back out, scrambled into randomness, through the very faint Hawking radiation that black holes are predicted to emit. We don't know the answer, Black holes force us to confront the limits of our knowledge. They are not just objects. They are edges. Edges of physics, edges of thought, edges of understanding. But perhaps that is what makes them so compelling. Not just their gravity, but their mystery. They remind us that the universe does not owe us easy answers, that some truths are wrapped in deeper truths, that we can come right to the precipice and still not see the bottom. So tonight, as your breath slows and your thoughts drift inward, imagine the inside of a black hole, not as a place of destruction, but as a place of ultimate depth. Not as darkness, but as a question. A place where the rules dissolve, where motion becomes time, where endings are beginnings folded in upon themselves. You cannot go there. You cannot come back. But still it exists. And the fact that such a place exists, hidden in the quiet centers of galaxies, is enough to stir a profound and lasting wonder. It means the universe has corners untouched by our certainty. It means we still have mysteries to fall into. But one final question waits in the deepening night. If black holes take in and hold so much, do they ever let anything go? Do they grow forever, or do they, too, one day come to an end? Let's float gently there, next, to the slowest, quietest loss imaginable, to the final, patient breath of a black hole. Black holes grow. This much seems certain. They feed on stray gas, on wayward stars, on entire companion black holes if they drift too near. When they merge, they don't cancel each other out. They add up. They become something larger, heavier, a deeper well in the fabric of space-time. Growth seems to be in their nature. A natural conclusion, then, might be to imagine them growing forever, becoming larger than galaxies, larger than galaxy clusters, an endless, dark sink at the center of reality, consuming everything given enough time. But to answer whether this is their ultimate fate, we must drift into the truly long life of a black hole. We must watch it not only feed and merge, but also wait, and ultimately change. Let's begin with growth. A black hole born from a collapsing star might be only 10 or 20 times the mass of our Sun. But if it resides in a dense cluster or the gas-rich center of a galaxy, it can begin to accrete, to pull in matter. This process is not a silent plunge. The matter, governed by the conservation of angular momentum, spirals in, forming a brilliant, furious accretion disk. It heats up, radiates X-rays, shines with immense energy as a final testament before it disappears over the event horizon. This glow is how we find many black holes, not by seeing the dark thing itself, but by the light of its final feast. There is, however, a limit to this gluttony. If a black hole tries to pull in matter too quickly, the intense radiation pouring out from the hot inner disk actually pushes back on the infalling gas, blowing it away. This balance is known as the Eddington limit, a kind of natural speed cap on black hole growth. It doesn't stop the growth, but it regulates it, ensuring it is often a slow, stately process over millions of years. Then there are the mergers, as we've discussed. A 30 solar mass black hole and a 40 solar mass black hole might become a single 68 solar mass hole, with 2 suns worth of mass converted into the pure energy of gravitational waves. This is how we think the supermassive black holes in galactic centers were built. Not all at once, but step by step, merger by merger, over the lifetime of the cosmos. And so they grow. Some to billions of times the mass of our sun, quiet giants holding whole galaxies in their gravitational sway, heavy beyond comprehension, yet invisible to the eye. But even these titans do not grow forever. Eventually, they run out of fuel. The nearby gas is consumed or blown away. The stars settle into stable orbits. Other black holes are too far away to merge with, and so they rest. The universe contains many such dormant black holes. They have eaten what they can, and now they wait. They are not dead, just inactive, still capable of flaring to life should a star or gas cloud wander too close. It may take millions of years for such an event to occur. a brief breaking of the silence before the stillness returns. But there is another way a black hole changes over cosmic time. Not through growth, but through loss. A whisper, a fade, a process so slow and subtle that for most of the universe's history, it was thought impossible. This revolutionary idea came from Stephen Hawking. In a brilliant stroke of intuition, he realized that black holes are not quite black. By applying quantum theory to the very edge of the event horizon, he discovered that black holes should, in fact, radiate. This process, now immortalized as Hawking radiation, allows black holes to slowly, imperceptibly, leak energy back into the universe. How can this be? The vacuum of space, according to quantum mechanics, is not truly empty. It is a seething, frothing sea of virtual particles. Particle-antiparticle pairs constantly blink into and out of existence, borrowing energy from the universe for a fleeting moment before annihilating each other and paying the energy back. This is happening everywhere, all the time. Now, imagine this happening right at the event horizon. In a fiendishly clever bit of physics, one of these virtual particles can fall into the black hole, while its partner escapes into outer space. The escaped particle, now real and unable to annihilate with its partner, carries away a tiny amount of energy. And where does that energy come from? It is borrowed from the mass energy of the black hole itself. So, a black hole slowly loses mass by radiating a faint, thermal glow of particles. It is not a fire, not a blaze. It is the slowest possible trickle, a soft, near-eternal exhalation of energy back into the cosmos. The rate of this evaporation is inversely related to the black hole's size. The smaller the black hole, the hotter it is and the faster it radiates. A black hole with the mass of a small mountain might radiate away all its energy in a flash, over a time span much shorter than the current age of the universe. But a black hole of stellar mass? It would take far, far longer than the 13.8 billion-year age of our universe to evaporate even a tiny fraction of its mass. A supermassive black hole? The timescales become truly astronomical, on the order of 10 to the power of 100 years or more, a number so vast it defies all human intuition. Still, Hawking's idea was profound. It told us that black holes might not be eternal, that even the darkest, most permanent-seeming structures in the universe are, on the grandest scales, transient. They too will one day fade. So we arrive at an answer, not simple but quiet and profound. Black holes grow, they merge, they feed, but they also wait. And in the farthest, coldest stretches of time, when the stars have long since burned out and the galaxies are dark, they begin to fade. Not from an explosion, not from a dramatic decay, but from a long, slow release of quantum breath into the ever-expanding cold. Imagine it. Trillions upon trillions of years from now, in the dark era of the universe. The last stars are dead cinders. The galaxies have evaporated. Only black holes remain, the last macroscopic structures in a cosmos growing cold and dark. And then even they begin to go. One by one, a whisper at a time, they release their mass, their curvature, their story, back into the universe as a faint bath of radiation. The smaller ones go first in a final, bright flash. The supermassive ones persist the longest, glowing with a temperature only slightly above absolute zero. It is the softest kind of ending, not a destruction but a return, a dissolution. Black holes do not rage against the dying of the light. They simply exhale, and the space they once curved so violently becomes still once more. And what happens after that? If black holes fade and ordinary matter is gone, what is left? Only an ever-expanding, ever-cooling emptiness, populated by a sparse sea of photons and subatomic particles, their energy stretched to near nothing by the relentless expansion of space. A universe of memory, but not of substance. A quiet, final chapter. And so we have traveled far together. From the first whispers of the night sky to the fiery death of stars, from the patient dance of merging black holes to the echoes of the early universe, and finally, to the quiet evaporation of the cosmos's last dark sentinels. We have drifted through time and space and come to rest at the edge of everything. This journey has been one of scale and wonder, but also of a deep, abiding peace. The universe is vast and often violent in its processes, but it is also governed by a beautiful, elegant order. It operates on timescales that humble our brief lives, reminding us that our moment here, though fleeting, is a part of this grand, unfolding story. You are made of stardust, forged in the hearts of long-dead suns. The gravity that holds you to your bed is the same force that anchors galaxies and orchestrates the cosmic ballet of black holes. The very space around you is a flexible, dynamic fabric, still trembling with the memory of ancient collisions. As you lie here now, let go of the need to solve, to understand, to know everything. Let go of light, let go of gravity, let go of time. You are safe. You are still. You are part of a universe that holds you, even in its immense silences and its deepest mysteries. Feel the weight of your body on the bed. Listen to the rhythm of your breath. Your mind, which has wandered so far across the cosmos, can now spiral gently inward, toward rest. If your eyes are heavy, if your thoughts are softening at the edges like distant galaxies fading from view, that is just right. It means you have listened long enough. You have wondered wide enough. Before you drift off entirely, if this quiet journey through the stars and shadows has brought you a moment of peace and wonder, I would be so grateful if you'd give it a gentle like, or even subscribe for more sleepy stories like this. It helps other quiet minds find their way here. And if you feel like it, leave a comment telling me where in the world you're listening from. I love watching this map of sleepy listeners unfold, a constellation of shared calm across our planet. Thank you for your curiosity. Thank you for your stillness. Thank you for your company. Wherever you are, whatever you carry from your day, know that the universe carries you too. Sleep well, and I'll see you next time in the space between stars. Hello and welcome. Find a comfortable space wherever you are. Let the day's tensions soften and allow your mind to grow quiet. This is a space for wonder, a gentle journey through the hidden rhythms of the cosmos. Tonight, we explore a simple, profound truth. Nothing is ever truly still. As you lie there, your body seems a portrait of calm. But beneath the surface, a universe of motion thrives. Your blood travels its looping highways, a silent, pulsing river within. Your lungs draw in the world and release it again, a soft bellows. Delve deeper to the cellular level and you'll find a frenzy of activity. Proteins being built, signals firing, the very machinery of life in constant, bustling operation. Go further still to the atomic realm. Here, the electrons that constitute your being do not orbit like placid planets. They exist as a blur of probability, a vibrant cloud of potential, forever dancing. Even if you could command every muscle to absolute zero movement, this quantum hum would remain. It is the baseline energy of existence. You are, in your most fundamental nature, made of motion, and you are not alone in this dance. The planet you rest upon is spinning, a colossal sphere turning at over 1,000 miles per hour, carrying you through the star-dusted void. This spin gives us the gentle rhythm of day and night, a cosmic heartbeat so steady we rarely feel its pulse. But Earth is also in flight, orbiting our sun at a breathtaking 67,000 miles per hour. This annual journey is a silent, graceful carousel ride around a central fire. And the sun? It is not a fixed lantern. Our star, with its entire planetary entourage, is adrift, pulled by the gravitational embrace of the Milky Way galaxy, a swirling pinwheel of hundreds of billions of stars. We are tucked away in one of its spiral arms, a tiny passenger on a great galactic merry-go-round. It takes us a staggering 230 million years to complete just one loop around the galaxy's heart. And the galaxy itself? It sails through the expanding universe, a ship on a dark, unimaginable ocean. So, you see, stillness is a beautiful local illusion. It is a trick of perspective, a momentary pause in your personal story while the grander narratives of physics continue unabated. A tree seems still, but it grows toward the sun. A mountain feels eternal, yet it rises and erodes by inches every year. Time itself is a form of motion, a river you cannot see but always feel, carrying the future into the now, and the now into the unchangeable past. What drives this ceaseless motion? Invisible, mighty forces. Gravity, that quiet tug that binds planets to stars and keeps your feet firmly on the floor. Electromagnetism, which lets atoms bond and your heart beat in a coordinated rhythm. The nuclear forces, tucked into the sun's core, driving the fusion that warms your face each morning. And beneath it all, the quantum motion, the restless fabric of reality itself. Every breath you take is part of this cosmic chain. The air you inhale joins your body's rhythm. The air you exhale is released back into the vast, circulating winds of the planet, eventually touching leaves, clouds, and distant shores. You are not a solitary being in a static room. You are a note in the universe's endless song, connected to volcanoes, rivers, and stars being born in far-off nebulae. Perhaps this is why music resonates so deeply within us. It echoes a truth we carry inside. Life is made of cycles, of waves, of beats. Your heartbeat, your brainwaves, your breath. They are all part of the universe's rhythm. And light, yes, even light is in motion and it never, ever stops. Let's lean closer to that invisible hum now, to the hidden threads that hold motion and space together. You lie in your bed, surrounded by blankets, supported by a mattress, all feeling solid and steady. But beneath all that comfort is something deeper, stranger, and more fundamental. You are resting on the very fabric of the universe. Physicists call this fabric space-time. It doesn't feel like fabric. You can't see it or touch it. It's not made of atoms or particles. It is more like the stage on which everything unfolds, the unseen theater where matter performs and time keeps the beat. Every step you've ever taken has pressed gently into it. Every breath you draw is measured by it. And this stage is not flat. It bends. Close your eyes and imagine placing a heavy bowling ball in the center of a soft, stretched trampoline. The trampoline sags deeply beneath the weight, creating a curved valley. Now roll a marble near the edge of this valley. The marble doesn't travel in a straight line. It spirals inward, following the curve. This is how mass affects space-time. Everything with weight, from your body to the Earth, from the sun to a galaxy, causes this invisible fabric to curve around it. This gentle bending is what you feel as gravity. It is not a mysterious force pulling you downward. You don't fall to the Earth because it pulls you. You fall because the Earth's mass curves the fabric of space-time beneath you, and you are simply following the path of least resistance, like the marble rolling into the valley. You are, in a very real sense, sliding down an invisible slope created by a planet. This bending affects everything, even light, which has no mass at all. A beam of light traveling near a massive object like the sun doesn't slow down. It follows the curves of space-time, travels straight from its own perspective, but space-time itself isn't straight. It dips and warps around stars and planets and, most extremely, black holes. This strange idea that space can be bent without breaking is the language of Einstein's great insight, his theory of general relativity. It gave us a new way of seeing the cosmos, not as a void with things in it, but as a dynamic fabric shaped by the presence of mass and energy. And time is woven into this fabric, too. It is not separate, not ticking away on its own. Space and time are a single entity, space-time. Just as space bends near mass, time stretches. Near a massive object like a planet or a star, time moves more slowly. It's a tiny, almost imperceptible effect, but it is real and measurable. This is why astronauts on the International Space Station, orbiting high above Earth in slightly weaker gravity, experience time a fraction of a second faster than we do on the surface. Their clocks literally run faster. They return to Earth just a tiny bit younger than if they had never left. You live your entire life in this woven, curved, dynamic fabric. It is invisible but always present, holding you not tightly, but with a quiet, patient grace. And this fabric is moving. The universe is expanding, not into something, but from within itself. The fabric of space-time is stretching, like dough rising in a warm oven. The galaxies are not flying away from each other through space. They are being carried apart because the space between them is growing. As space expands, time flows forward, never backward. And this gentle, steady unfolding is what allows the universe to exist at all.